So just for the record, I'm starting 4 minutes late. Actually, 5 minutes late. Okay, so last time I wanted to say two things, but I probably said -1. So today I have to say 5 things for us to be on the schedule. So the first thing I want to say is how do we add equations? In physics jargon, this will be called chi-h multiplet. Also known as Cazule complex. And then I want to talk about the global versus local symmetry groups, or how to compute using symmetries. And then we'll go back to what I left off at the end of last lecture, the modular spaces of instantons. And their compactifications. And their symmetries. And the fixed points of the symmetries. That has to do with the ways to compute things. And from that, we'll get to the instanton partition functions. And finally, I will talk about the Y classes, or Y observables. Okay, so now I don't need this anymore. Okay, so last time we started setting up the technology for doing some simplified path integrals using supersymmetry, the twisted supersymmetry or Q charge. And so we had nilpotent operation acting on the space of fields, which squared to 0, which should be viewed as a differential. Is there a question? Okay. So so we had some fields which I was denoting by letter x. So these are coordinates on some space, and Q acting on x gave a fermionic partner, one form. So this is like dx in ordinary notation. And then Q acting on psi, so there's some space, there are some coordinates which I'm skipping the labels. Gave the vector field, which depended on which was linear. It's a linear function on Lie algebra. So this is a symmetry group G with the Lie algebra little g. And the objects on which my operator Q is acting should be G invariant. So you're allowed to have some expressions which depend on x, psi, and sigma. And then I also introduced sigma bar, which transformed into eta. and eta transformed into the commutator of sigma and sigma bar. So the requirement was for this gamma to be G invariant. Actually, this is the only pen which we... Ah, okay. So this should be G invariant. And on G invariant functions, Q squares to 0. So if you just apply Q twice to, let's say, X, you will not get 0. You'll get the vector field. But if X enters some function which is G invariant, then Q squared would be the action of the vector field generating the action of the group on the function. And if it's G invariant, it will annihilate this function. So now I want to be able to impose some constraints on my variables X. And so to impose constraints, say some equations S A of X equals to 0, some number of equations. So we can either try to solve these equations and get, instead of the original variables X, we'll get some parameterization of the space of solutions, and then we'll replace everything we had before by now the parameters on the space of solutions of these equations. Or we can actually work on a bigger space and impose these equations homologically. So in other words, we will introduce new variables, additional variables. So new multiplet, chi and h. So if my equations are bosonic, then the variable chi will be fermionic, and vice versa. So let's, for simplicity, talk about the ordinary equations, which are even. So then chi will be the fermion, and my transformation, my differential Q extends to these new variables in the following naive way. So here I'm assuming, I'm allowing for my equations to transform under the symmetry group. So I want to be able to impose these equations while preserving G invariance, which means that my functions as, well, they're actually not functions, they can be sections of some vector bundle over the original space X. Space X sounds funny nowadays. So there is some, so I want to think of my equations as of a sections of some G equivariant vector bundle. And so this R of sigma is a representation, it's the action of the group on, well, the infinitesimal action of the group on the fibers of my vector bundle. This is not, of course, the full formula, because that's sort of assumes that the bundle is trivial, and the action simply happens in the fiber. In fact, this should be written more carefully in taking into account some choice of a connection on the bundle, so that this term, for example, would have to be extended to something like AI AB psi m chi b. So here, so A is a connection form for this vector bundle with some choice of a connection. You can understand why you need this correction term involving connection term by thinking about trying to change coordinates. So if you go from coordinates x to some other coordinates in some local patch of the space x, and then you think that there is some lift of this transformation of coordinate transformation to the to E, so naively chi will transform with some will be multiplied by some matrix which depends on x, and now since x is not Q invariant but rather picks up transforms into psi, the equation when Q of chi is equal to h will not be coordinate covariant. Or in other words, so H should transform not as a section of a vector bundle, but as a section of a affine bundle. And so we add the connection to make H again a section of the same bundle E. And so then it will propagate further. So there will be some curvature terms. Of A now acting on, so there will be 2 psis and chi. I will not write this explicitly. We will not be dealing with really curved spaces. The space which we will be interested in will be the space of connections, which is actually a fine infinite dimensional affine space. So all these subtleties play no role in this course. But you just should keep in mind that in general, those terms are present. And in fact, if you want to do the exercise number 1, I think you actually will need those terms to derive the Gauss-Bonnet. I forgot what, I think it's Gauss-Bonnet formula. Yes.
When you say complex, in a complex, the differential usually raises degree by 1.
Yeah, so chi has degree -1, and h has degree 0. Sigma has degree 2. R is neutral, so yes.
Oh, and R is linear.
Yes, it's the representation of the representation of the Lie group in the fiber.
Maybe I'm not understanding. I thought Q squared is supposed to equal 0, but just from the formulas you do down here on the right hand board. Like
Well, just read this line again. Then.
No, but on the right hand board, you have Q pi equals h. Oh, I see. But,
Again, this is just, so these are some, well, I mean, what's the difference between the left-hand side and the right-hand side? It's the same thing. So Q squared is a infinitesimal transformation generated by sigma, but when you act on functions which are G invariant, Q will square to 0. So now what I'm saying is I'm now extending the allowed functionals to also contain chi and h, and then effectively when we will be doing the integration, we can actually add a term. So remember, yesterday we were talking about integrals which were like integrals this type. So we had dx, d psi, d sigma bar, d eta. And now I will also have, I guess I'm now integrating over the total space of my bundle E. Well, okay, I should say, I want to say it as, so P E cross G. So what I'm doing, I'm taking the total space of E, I'm reversing the parity of the fibers, and so that's what, so x and chi together, they are the coordinates on pi e. Then I'm taking the, and so g, so sigma bar is a sigma bar parameterizes g, and then I'm taking the tangents bundled to all of that and reverse the parity of the fibers. So that will, so that what psi, h, and eta are standing for. So they parameterize the fibers with reverse parity. So sigma bar parameterizes g. All right. So now we had some class. Somebody gave us this class omega. Yes. No, not yet. So this is where the SA will enter. So SA will enter the definition of the class which we'll be integrating. And now, so we had some mu class yesterday which had to do with the trying to fill the volume of, trying to provide the volume form for the orbits of the group G, which I will keep for the moment unspecified. And now I want to impose the equations. I want to impose the equations inside this integral. So how do I do that? I put e to the I, and then I put q applied to chi a s a. So if I do that, if I do just that, if you compute q applied to this whole expression, this is exponential I h s plus or minus, because we are going through the fermion, minus chi ds dx psi. And there are other terms which I will the terms involving connections I will skip. Well, actually, I can just write it as a covariant derivative. Chi is a fermion. Chi is a fermion. So if S is a boson, so the parity of chi and S are opposite parity. For bosonic S, chi is a fermionic, and H is a bosonic. So pi means the reverse parity. So chi is a fermion. If X is a boson, chi is a fermion. So this is fermion if S is a boson. And so what you see here is just an integral representation for the delta function. So if I integrate over H, I'll get delta function of S. And now if I integrate over chi, I'll get some product. I'll get some well, kind of fermionic delta function of psi times nabla S, which really what it does, it constrains the now tangent directions in the base to be those which are in the kernel of the covariant derivative of the section. So I'm sitting. So my bosonic coordinates x are constrained. So this is space x where I'm sitting, and this is the zero locus of S. And so the delta function of S, which I will get by integrating out H, tells me that X should belong to the zero locus. And then the integration over chi tells me that the psi's, so what are psi? Psi's are kind of infinitesimal variations of X. So they're like tangent vectors and so the integration over chi tells me that the psi's should also be tangent to the zero locus. Okay? So this it's a caricature. So x sits on the zero locus, and psi is tangent to the zero locus. So that's what these two integrals give. Now, this would not be very useful unless there was some way of deforming this integral to make it less sharp as far as the equations are concerned. Because after all, we don't really want to solve these equations, because if we could solve these equations, we would solve them and be done. But solving equations is hard. So we're trying to instead of solving equations, we want to be able to integrate over the zero locus, but without actually solving the equations. And so the idea, which goes, I mean, topologically it goes, I guess, back to Tom, is to somehow smear the zero locus. So instead of really imposing it, let's replace it by some kind of a measure which has a which integrates to 1 when you integrate across, but is not that sharp. And then maybe ultimately smear it so that you will actually integrate over all of the space x without changing the integral. And so the idea is to use the fact that our class omega was supposed to be Q closed, and also use the fact that we can integrate by parts in the sense of Q, so that the integral of Q exact things is equal to 0. And so modify this expression. So this is where this is why it's useful to have this Q symmetry, Q supersymmetry. So now add a term with some parameter t, some metric. Sorry. So here I need to choose some metric on the fibers, which would be G invariant. So GAB is the inverse metric. So it's a metric, G invariant metric on the fibers of E. So now what will happen is that now when you apply Q to this expression, you will get this guy times exponential minus t norm h squared, and then something like some terms involving chi, nabla chi, and some curvature terms. So this curvature, it's a curvature of a connection on E. So it's a curvature of E, not of the manifold. So now if you integrate out H, instead of delta function of S, you will get so integrate H out, and you'll produce exponential of minus norm S squared divided by T. And you'll get some curvature terms. So if you send T to infinity, so if just the first application of that is the usual identity which expresses the Euler class of a bundle. So the Euler class of the bundle E, you can represent as a Poincare dual to the zero locus of a generic section. So that's one way. Or you can represent it using curvature of a connection. So send T to infinity, then effectively you forget about the section period. So section this. Oh, you send section to 0, which is the same thing. And then instead when you integrate out chi, you will get a bunch of curvatures. And so curvatures will form something like a Pfaffian. And so that will give you another class in the same cohomology of Q. It will be class of in the cohomology of the base X, which will represent the same order class of the vector bundle E. And so that's the exercise, actually, one of the exercises which I gave to work it out in the example when E is actually a tangent bundle, and the section is some vector field on the manifold. So in that case, the connection which you could choose is the connection which you let's say get from the metric on the manifold. So that's the prototypical example of a calculation which we will be doing over and over again in four-dimensional gauge theories. So one of the things which we'll be doing will be forgetting about the equations which are complicated to solve, but try to push all the calculations towards these curvature type integrals. And the curvature type integrals will be calculated using the number 2 on my list today. Yes? Yes. So if you good. So if you do so if you spell out what does it mean to integrate H in this formula, well, so this variable H enters my integration problem quadratically in exponent, and so so integrating over H literally means just finding a critical point. And for the critical point, H is up to the metric, and the factor of T is the section. And so now if I substitute, so this is called, physics is called going on shell. So now if I substitute that value of H into my differential, what I'm getting is that now Q applied to chi up to some non-degenerate matrix is the section. And that's Koszul complex. So now I have my original functions. I enhanced. So my original functions sit at the 0th term of a complex, which now has negative components. So the -1 degree component will be functionals which are linear in chi, -2 functions which are quadratic in chi, and so on and so forth. And I have a differential which goes from so -1 to 0. So these are linear in chi functions, these are chi, and so on. So these are no chi's. So these are just functions of x, psi, sigma, and sigma bar in eta. And here I allow 1 degree of chi, 2 degrees of chi, and so on. And now the differential will send chi in here proportional to s of x. And so that's what Koszul complex does. It imposes the equations homologically. So now, if you like, the functions of x which are proportional to the equations will be q exact. And so we divide by them. Yes. Yes.
So somehow the Koszul complex is really only relevant, I think, both for mathematicians and physicists if the section is sufficiently transverse. So in your applications, are you going to leave that for us as homework to check that the section is transverse?
Well, that formalism takes care of that, because if a section is not sufficiently transverse, the curvature will picks up, and so that enters the story. It's well, you have cohomology in other degrees, presumably, if And so I'm happy with it. Well, it's well, if you start with that, then you really are messed up, because now q squared will be some derivative of s times psi. There's no obvious principle to make q differential. It will not be nilpotent in any obvious way. In the standard, in the Kazul complex, which mathematicians study, x variable is q closed to begin with. There is no psi. So this is some kind of differential version of Kazul complex. Derivative? First we do Kazul complex, and then we make things equivariant. Stack. Well, maybe I'm not sure. I don't know how to do this. So I'm just trying to. I'm interpreting in the simplest possible terms what the supersymmetry algebra does actually. So that's okay. All right. So that's part one. So that we now know how to impose equations. Maybe partly. Now I want to talk about, so let's forget about the equations for now. Just again, let's do the simplest case when all equations were already solved. And let's just discuss how we can use equivariance to compute things. And that's, and so that's the following idea. So suppose X, again, is a G space. So the group G acts on X, and suppose omega is a G equivariant form. So remember, it means that this is a function on the Lie algebra valued in differential forms on X, which is G equivariant. And moreover, let me assume it is Q closed. So d plus IV of sigma applied to omega is equal to 0. So I now want to integrate, and suppose the integral of omega over x exists. So what does it mean? So omega, well, it's a function of Lie algebra, so I can substitute sigma and get an ordinary differential form on x. And so what I do now, I take the top degree component, so the component of degree dimension of x, and integrate over x. And so this way I will get something which I will call the partition function. So only top degree matters. So what can we say about this function? So it's a function on the Lie algebra, and by definition, well, it's holomorphic of sigma because sigma bar doesn't enter. It's holomorphic in sigma. It is holomorphic in sigma. Sigma bar doesn't enter. We can actually slightly generalize this. We can say that we can allow a sigma bar dependence. So let me introduce a more general object, a function of sigma, sigma bar, and eta, which is the integral of x over x of equivariant differential form of a more general type when we allow sigma bar and eta dependence. So I still want omega to be Q closed. So now d plus so now I want omega to be killed by this extended differential. Again, I'm sorry. Yes. Yeah, because I don't like this formula, so that's okay. I'll write it here. Say it again. So it's a functions on G valued. If you like, I can write. Yes, that's what I had yesterday. So functions on G valued in this space, or I mean, if you want, you can write it as it's just that in my notation was more convenient because it reminds you that when you substitute sigma, you get a differential form on x. So what can we say about this function of sigma? Well, first of all, it is G invariant. Right? Because remember, omega was supposed to be G equivariant. So omega of conjugated sigma is the same thing as pullback of omega of sigma with respect to G. And now doing pullbacks, doing any diffeomorphisms under the sign of integral don't change the sign of an integral. So this partition function is actually a function only on the conjugacy class of sigma. So you can compute it to what? Yeah. So to compute it, it's enough to know its restriction onto the maximal torus. So z of sigma is determined by restriction by its I have a slightly unconventional notation for the maximal torus. So T is the Lie algebra of a maximal torus G, where it still there is some remnant of this condition which is the Weyl invariance. So Z is some Weyl invariant function on the maximal torus. And just like the characters, so Z, in some sense, is some kind of a character of the group G. So we should think of is a character. Okay, but now the great thing about this function is that not only it is W invariant, it is actually, it's almost computable. And why it is computable? That's because we can use the same trick of modifying the integrand by inserting something Q exact. Here for some choice of R. And so now let me make the choice of R, which will make this integral computable. So choose a G invariant metric on X. If G is compact, we know it exists. And choose an element sigma bar in the Lie algebra. For the moment, just choose any element, and then we'll make well, choose an element such that so this, if my metric is denoted by brackets, the norm, the scalar product of V of sigma with V of sigma bar is positive definite. It's not negative definite. Yes, V is a vector field which generates a group action. So V is a homomorphism from G to the vector fields on X. So my R would be here's an exercise in these complicated notations which I introduced. So R is negative G M n psi m V of n of sigma bar. Vn of sigma bar. So it's a one form. So G is this metric, yes. So this is it's the metric which I denoted by round brackets. So this is the invariant notation. It's a one form, which is the scalar product of a given vector with the vector field V of sigma bar. And this is the same thing computed in coordinates. So, so G Mn is a scalar product of the coordinate vector fields. And then I want to multiply it by some number t. So there is some parameter t in my problem. So now Z of sigma is the integral over x of this old guy omega of sigma, and now it is multiplied by exponential of minus t, the scalar product of V of sigma with V of sigma bar, plus t, and then something like G Mn psi m, covariant derivative of V of sigma bar psi k. So what I have here, so this is some function on the manifold X. This is a two form because it has two sides, and this is multiplied by omega. So now I need all of the omega. So omega, remember, may have had components of different differential form degree on X. And so now when I will be expanding my exponent in the powers of this two form, not only the top degree component of omega, but lower degree components of omega will also contribute. And if I expand this to the maximal power, which is the dimension of x over 2, then it will be the lower degree, the zero component of omega, which I will need to do the integration. Now, the beautiful thing here is that the left-hand side does not depend on t, because t was never there in the first place. So now I can play with the parameter t. And so if I send t to infinity, depending on how you choose sigma bar, if you choose sigma bar to be equal to sigma, or sigma, rather, if you choose sigma bar to be sigma complex conjugate, then this is essentially norm squared of the vector field v of sigma, multiplied by a very large number. So your integrand is now highly picked near the fixed points. So these are the points where v of sigma vanishes. And everything else is highly suppressed. So by taking t to infinity, we derive the following localization formula. So let me assume that v of sigma has only isolated zeros. I mean, it doesn't have to be. You can, from this, you can easily generalize to the case when the zeros are not isolated. So at each zero, so let's p be such a zero. So v of sigma at p equals to 0. Then locally, you have the following structure. You have the following picture. So this is p. This is my tangent space to x at p. And then this is the space x around it. Now, remember, I said that my sigma, we can choose we can choose a torus in which we take sigma to belong to. And now, so if this is my group G, and then there is a torus inside this group, so this is the maximal torus of the group. And then sigma is some generic element of the Lie algebra. So it's some infinitesimal, generates some infinitesimal torus rotation. So if you exponentiate, it's a different t. So let's call it lambda. You'll generate a one-parametric subgroup of the maximal torus, which for generic choice of sigma will be an ergodic subgroup. So not only this point P is fixed by sigma, it is fixed by all of this torus. And therefore, the torus acts, so the torus acts on the space X, but preserves the point P. So it will act linearly on the tangent space to this point. And so this tangent space will split as so Tp of x will split as a sum of the two real dimensional irreducible representations. So these are irreps of the maximal torus. So the so Tp of x is a representation. So this is a linear representation of the torus, and as a linear representation, it splits as a product of irreducible representations, which are two real dimensional. So in formulas, what I'm talking about is that so if you look at the components of a vector field, so Vn is a function of x, so it's a function of sigma, and now it is a function of x. So these functions vanish at the point P. So now it's you can the linearization. So the first derivatives of these functions are well defined. You get some matrix of the derivative Vn dm at the point of sigma at the point P. So this is the matrix. So this is the matrix representing sigma in the morphisms of the tangent space to my space X at the point P. And now these subspaces are just eigenspaces. Well, the not quite. So these are invariant subspaces of this matrix. So this matrix splits. There is a basis in which this matrix will have a block diagonal form. I don't write here. I'll write. So the matrix dnVm of sigma has a block diagonal form 0, 0, 0, 0s. And now each block has the form 0 w of sigma minus w. So wi of sigma minus wi of sigma, 0. And so I goes from 1 to dimension of x over 2. If x is not even dimensional, then obviously the well, not obviously, but by thinking about this picture, you will understand that a vector field cannot have isolated zeros. So it will either have no zeros, or the zeros will form at least one real dimensional curves. And so then this picture will be in the normal direction to such a curve. So so these functions wi of sigma, these are linear functions. Linear functions. And moreover, in some normalization, they actually integral linear functions. The coefficients are all proportional. So the ratios of coefficients in some basis in the Lie algebra would be rational numbers. That's because this action of this infinitesimal action actually leads to the action of the group. And so there is a torus, the group torus representation. And so these representations are rigid. And so it is this data. This is the only thing which you need to know about this fixed point. Well, I'm slightly simplifying. There is some. You need to know something about the orientation. And I believe that was a question which was raised at the end of the previous lecture. But so I will sweep it under the rug for the moment. So here, you see, this w, by this formula, the w is defined only up to a sign. And in fact, you cannot define individual w's uniquely. But what you need for the formula, so this final formula says that z of sigma is the sum over all such fixed points. And then at each fixed point, what you do, you take omega of sigma, which is our equivariant differential form, which is now in a homogeneous differential form. You take its 0-degree component, which is just a function, restricted at the point P, and then divide this by the product of these linear functions. These are called weights. So your result is that, so this is the result, this is the whole thing. So it's this is the fixed point formula. So it appears that you need to know very little about the manifold. You only need to know about the fixed points of the torus, the maximal torus action on the manifold X, and the linearization of this action near each fixed point. So what you see in this formula is the product of W's. So even though the W's themselves were defined up to a sign, you can actually define the product of the signs. So the individual signs you cannot define, but the product of the signs is well defined. And that's the orientation of the manifold, which keeps it there. So the famous example of this formula so the example of equivariant form, actually, of omega of sigma is for symplectic manifold X, if X is symplectic, it's below the waistline. Okay, so let me. So suppose X is symplectic, and there is an action of the torus which is Hamiltonian. So each vector field Vn, V of sigma, so omega is a symplectic form. So each vector field comes from a Hamiltonian, which is linear in sigma. So H is known as a moment map. Okay, now it's torus. The moment map. So then the example of the equivalently closed form, the omega of sigma is exponential of capital omega plus h of sigma with minus. So that's the definition. That's essentially the definition of a moment map. And so then application of the formula says that the integral, so z of sigma is on the one hand, it's the, so if it's dimension to n, it's omega to the n over n factorial. This is symplectic volume multiplied by exponential of minus h of sigma. So that's an integral which you would normally consider in statistical mechanics as a partition function of a statistical mechanical system for which X is a phase space. And then this formula says that this is equal to, it's exactly given by this stationary phase approximation. So it's a sum over the fixed points, which are the critical points of the Hamiltonian. And then you just evaluate h of sigma at each point P, and essentially this product of the weights will be essentially the square root of the Hessian of h properly normalized, properly divided. So the square root will actually have signs, and the signs are determined by the formula. And this is called the Sturmat-Heckman formula. Yes, so this is the Sturmat-Heckman. It was originally discovered actually as a feature, is a statement in symplectic geometry, when Hans Döstermatt and Heckman, they studied the dependence of the class of the symplectic form on the symplectic quotient. So if instead of looking at x, you take a symplectic quotient with respect to t and look at the class of a symplectic form as a function of the value of the moment map, we discovered that this class was linear in the level of the moment map, and that allows you to evaluate this integral explicitly in those terms as an integral of some exponential of linear function on a kind of a polytope. But then ITIA and BOT, they... Okay, so the... Okay. Okay, thank you. So I read the paper by ITIA and BOT who so okay.
But BOT, in fact, did these formulas in 1967. That's worth noting.
Okay.
BOT, in fact, knew these formulas much earlier.
So this is, but for physics, this is of course, it all goes back to Weyl, actually, because this is just a quasi-classical limit.
Well, okay, but you're going to say it's due to ITIA and BOT.
I'm not saying, I didn't say this is due. You didn't let, Ezra, you didn't even let me say anything, because I was saying that ITIA and BOT developed this equivariant cohomology theory to put this formula in the context. I apologize to late. No, Dostematic, you just stepped out when I was explaining this. So Dostematic Heckman derived it using, you were studying the class of a symplectic form of a symplectic quotient. And so they didn't know any of this. All right, so so this is how we compute things. And what I meant by this slogan was that there are two kinds of groups which we encounter. Some groups we divide by, and on the quotient they no longer appear as symmetries. They appear as some kind of topological complication of the quotient space. But there are groups which we keep as a symmetry group, and we use them to compute things. So so what you can conclude from this formula, which is kind of remarkable, is that now if you forget everything I said before, but just simply stare at this formula as a function of sigma and take a limit, sigma goes to 0, then on the left-hand side, you have an integral of an ordinary closed differential form. And so it's a symplectic volume. But on the right-hand side, you still have a fixed point formula. So here, when I say dh of sigma, I really mean just sum of fixed points. And when you're do things carefully, you will see that this is, so there's some limit when sigma goes to 0, which exists. And here you just have the nth power of the Hamiltonian divided by the square root of the determinant. Again, plus minus 1, plus minus sign over n factorial. And remarkably, the sigma dependence drops out. I mean, it should for the left-hand side, because on the left-hand side we don't have it. And so what it means means that we computed the ordinary integral using the symmetry in terms of the fixed points, even though it was not obvious that, I mean, the left-hand side, if you think about this as a measure, the measure is kind of spread over all of the manifold. But the right-hand side, again, only knows about the fixed points and some linearization of the group action near the fixed point. And so this is the usefulness of the equivariant cohomology. If you view it, so if you view equivariant forms as deformations of the ordinary differential forms, deformation parameters being the sigma, so the parameter of the group, that opens a way of computing integrals, which normally you would have a hard time dealing with. And so that's a strategy of most things which follow. Now, famous application, Ezra is going to kill me, but okay, famous application of this formula is in the infinite dimensional case when you take X to be a loop space of a Riemannian manifold. Maybe we should ask Ezra about it. So if you take X to be a loop space of a Riemannian manifold, then you can formally so then you can define a kind of a symplectic form. It's almost symplectic form. It's not really. It's not. Unfortunately, it's not non-degenerate as a symplectic form should be. So it's a two form on the tangent space to the loop space, and so the points of space X are loops in Y. So this is the point in X space. And so the tangent vectors to X are vector fields which are tangent to Y, defined only along the loop. So this is Xi, and this is eta. So what you do, you take the vector field Xi, you take a covariant derivative along the loop. So there is a tangent vector along the loop, and the metric allows me to do covariant differentiation and take a scalar product. In physics notation, this would be, so omega is the integral gmn psi m dt psi n. T, where T is a periodic variable, so it's a parameter on the loop. Say my loops are and now there is a group action. Well, the obvious group action, the group U1 acts on X by rotating the loops. So it just shifts the parameterization of my loop. X of t goes to x of t plus tau. And so now if you take this as a symplectic form, a little computation will show that the Hamiltonian which generates this action is the usual kinetic energy and now if you formally compute the left-hand side, that will be a partition function of a quantum mechanical, supersymmetric quantum mechanical system, which you can convince yourself computes the index of Dirac operator on Y, if it has spin structure. And then the right-hand side, the fixed point formula, will give you the ITS-Singer index formula. So the fixed points are constant loops. Sitting inside the loop space. Now, strictly speaking, so this is the case when the fixed points do not form an isolated, they are not isolated, they form the whole manifold Y. So you need a little small generalization of what I discussed, but this can be done and was done rigorously, and you can ask Ezra about the details of his rigorous proof. Right? But you wrote a book. I thought what was about this. Okay. Because it's an example.
No, on the loop space of Y.
Well, you need to do some computation to convince yourself this is a closed form. Now, for the Durstmann-Heckman formula, you actually don't need the space to be symplectic. I mean, all you need is for the form omega minus h to be equivalently closed. So that does not require omega to be non-degenerate. And this formula actually is not non-degenerate. So it is not exactly symplectic manifold. No, I mean literally in the sense that the contraction of vector field with symplectic form is equal to the. So here you don't need to invert the symplectic form to write this to verify this. Okay, so now we can go back to number 3, and I have 15 minutes. What is omega? Well, I mean, so there are all kinds of loops. So you can have a loop which has a cusp, and so then you will get the kernel in this case. For smooth loops, it has no kernel. Use yellow? Oh, sorry, I forgot. Yes, sorry. Distract. Okay, so now we'll be dealing with very specific manifold X and this and the bundle E and the equations. And so now we're back to the study of the solutions of the anti-self-duality equations on R4. So A is a UN connection, and I want my solution to be such that the integral, so the L2 norm of my so M4 is my for manifold, which I will eventually take to be Euclidean space. Yes, Euclidean space. So this is we want this action to be finite, and in fact it is thanks to the self-duality equation. And the self-duality equation, this is equal to 8 pi squared k, when k was the topological charge. So it's the first Pendragon class of the bundle extended to the compactification of M4. Class of the bundle P extended to the compactification of my four-dimensional manifold. So for R4, this will be just S4, the four-dimensional sphere. But here I'm using, so one thing to keep in mind is that, so this, so the star depends, in general depends on the metric on the manifold, but for two forms on the four manifold, the star only depends on the conformal class of a metric. And so this functional does not distinguish the flat metric on R4 from the round metric on the S4. So this is conformally flat. So that partly explains why we were entitled to the compactification of R4 by 4-dimensional sphere. Now, so we want to study the modular space, of solutions to the self-duality equation, modular gauge transformations G of x which approach 1 when x goes to infinity, and approach 1 with specific rate. So it turns out that there is a kind of Fourier transform which allows, well, it doesn't allow you to solve these equations explicitly, but it allows you to map the partial differential equations to matrix equations. So there is a Fourier NAM Mukai Corrigan Goddard transform. So it maps solutions, and also, of course, Atiyah Hitchin, Drinfield, Hitchin, Manning. To the linear algebra data. But this is actually based on the other D, which is Donaldson, which is also based on a B, which is Bailenson, which is also based on P, which is Penrose. I mean, this, and Ward. No. ADHM actually fixed some technical details in the constructions of these people. Yeah, maybe Donaldson sort of simplified this construction. So there's some beautiful geometry there, which I unfortunately I don't have time to explain. I advise you to ask Alexei Rosley about this beautiful geometry. It's you'll learn a lot. But so the construction, the linear algebra. It's a linear algebra with quadratic equations, so I don't know if it's still considered to be linear algebra. Anyway, so we have two spaces which I had time to introduce last time. So one of dimension k, another of dimension n. So these are complex vector spaces, and we will also endow them with Hermitian form. So Hermitian, both have Hermitian metrics, vector spaces. And now, so this is my space K, and this is the space N. And here's the data of linear algebra. So this is ADHM construction. We have the maps I and J. So I acts from N to K, J acts from K to N. And then there are two B's, or not two B's, so B1 and B2. And there are Hermitian conjugates. So there are also B1 dagger, B2 dagger, I dagger, J dagger, where dagger is defined using the Hermitian metrics, both on N and M space. And now, so there is a way to construct these matrices starting with an instanton solution. And this proceeds by solving the Dirac equation. Okay, this is too low. So the ingredient of this num, really this is num transform, is looking at the solutions of Dirac equation. Now, Dirac equation in the fundamental representation of the gauge group. So psi is a section of the positive chirality bundle valued in the vector bundle, which is associated with n space. So n is, as you can see, is the defining representation of un, of my gauge group. So this is n. I mean, you study the solutions for both equations, for both chiralities of spinors, and then you prove that the equation, assuming that A is irreducible, that is to say, the structure group of the bundle does not reduce to a subgroup, proper subgroup of un, then, so for irreducible, A psi minus is identically 0, and psi plus form a vector space which is isomorphic to K. So this space K is really just a space of solutions, of L2 normalizable solutions to the Dirac equation of definite chirality. And then when you have such a solution, what you can do, you can multiply this solution by the coordinate function. So let me choose some complex structure on R4. So let me denote by Z1 and Z2 the complex coordinates, holomorphic coordinates, and then Z1 bar and Z2 bar are the conjugates. So if you have a spinor, okay, maybe it's useful. It will be useful to say that this equation, if you rewrite it in terms of these coordinates, is equivalent to the following three equations: that f1, 2 is equal to 0, f1 bar, 2 bar is equal to 0, and f1, 1 bar plus f2, 2 bar is equal to 0. So this is for flat. So my metric has the form dz1 squared plus dz2 so squared. So this is my metric. And so this implies, in particular, that the covariant derivative in the directions, in the holomorphic directions 1 and 2 commute, and so do the covariant derivatives in holomorphic directions, in anti-holomorphic directions. And so so this is actually the starting point of the analysis, which leads to that beautiful geometry, twistors and so on. It turns out that well, I made some arbitrary choice of a complex structure, but you can actually do this for any choice of a complex structure, and then the parameters of the complex structure form a two-dimensional sphere, which enters the construction. Now, explicitly, the equations, so my spinors, psi plus minus, they have two components. They are so these are two-dimensional representations of the spin cover of the Lorentz group. So the Euclidean Lorentz group spin 4 is a product of two SU2 groups. And so these bundles S plus and S minus, they correspond to the two-dimensional representations of the left and the right SU2 factors in this decomposition. Sorry. And so for each, so the equations, so if I choose some basis, you can identify psi plus actually with the space of 0, 1 forms on C2. And so in this basis, the equations, the Dirac equation, will read as the following two equations. D1 psi 2 minus D2 psi 1 equals to 0. D1 bar psi 1 plus D2 bar psi 2 equals to 0. where d is a covariant derivative. So now, when we go off to infinity in our space, the connection form, the connection A, should approach the trivial connection. So up to gauge transformation, which might be singular at infinity, essentially the gauge field goes to 0. And so the solutions of these equations should approach the solution of the equation of the ordinary Dirac equation without any gauge field. And that equation you can solve very easily by writing an ansatz psi1 equals d1 of some function phi, psi2 equals to d2 of some function phi. So that will automatically solve the first equation. And then the second equation would tell you that the Laplacian of phi is equal to 0. And so phi has to be regular near infinity, which the first simplest solution would be essentially 1 over r squared. Well, then you can observe that you don't have to, so you can choose another ansatz for which psi1 is equal to d2 bar chi, and psi2 equals minus d1 bar chi. And chi also solves the Laplace equation. And so the solutions, there are two allowed asymptotic solutions for these equations, which you can combine together into something like, so psi1, psi2 behave as 1 over r to the fourth, and then some matrix I dagger z1 bar plus j z2, I dagger z2 bar minus j z1. And so I and j from this data are precisely recovered from the large X asymptotics of the solution to the Dirac equation. And psi minus vanishes. So this is the dual equation. And now to recover the matrices B1 and B2, you now take solution. So any such solution, and multiply it by the coordinate functions. So take z1 times psi plus, and then project back to the space of solutions, which you can do by multiplying it by the conjugate solution. I mean, it's Hermitian conjugate, and integrating over R4. So that will give you the matrix B1, and similarly, gives you the matrix B2. So you see, the operation of multiplication by coordinate functions commute when you act on all functions. But now if you restrict this operation onto a subspace of the space of, here I'm not talking about functions, I'm talking about the sections of spin bundle. So if you now, instead of looking at all sections of a spin bundle, you only look at those which are annihilated by Dirac operator, so you project on the kernel of Dirac operator. Out of commuting operators, you get something which may not commute. And in fact, and so this is the computation of Corrigan and Goddard, the commutator of the matrices B1 and B2 is not equal to 0, but it is equal to the product I times j. So when I and j are recovered from the asymptotics. So there is some, when you carefully do this computation, you'll do some Green's functions computations, and then you'll integrate by parts, and there will be some boundary term. And the boundary term will contribute that. In the work of Nahm, which is Werner Nahm, he was looking at this solutions of instanton equations on the four-dimensional torus. So there was no boundary. And there, his construction transformed the solutions of anti-self-duality equations on one torus to the solutions of anti-self-duality equations on a dual torus. So dual torus is the torus which is metrically, if your original torus is large, then the dual torus will be small. The radii of the dual torus are inverse of radii of the original torus. And so this is some kind of a limit. When the torus decompactifies, the dual torus shrinks to a point. Now, in addition to this equation, you can also compute the commutators of B's with B daggers. And you discover this relation. So these are the celebrated ADHM equations written in terms of the data of a specific quiver. So this is the quiver with one vertex and one loop. So when you unpack the structure, that's the structure which you will get. So I think my time is up. So tomorrow we'll proceed with analysis of these equations and what are the additional conditions we need to impose on the matrices for them to define non-singular gauge fields, and then we'll relax these conditions or modify them to produce some compactifications of the modular spaces, and then we'll be in position to compute integrals over these modular spaces using the fixed point formulas which I reviewed today. And then we'll introduce Y classes and so on. So, thank you. Yes?
So it looks as if you were applying somewhere the Ulenbeck-Yau theorem, that if the curvature is L2, then there's a gauge transformation, which is this, or you had something else in mind?
So what Ezra is referring to is Ulenbeck theory.
Oh, not Ulenbeck-Yau, sorry.
Ulenbeck theory. Yao didn't know about it. Yes, so the claim is that if you have a solution which is defined everywhere except at a point, then by perhaps making a gauge transformation in the neighborhood of that point, you can produce the connection which extends smoothly to that point. And so R4 being S4 without a point, if my solution, and yes, and the assumption is that the energy, I mean the action, Yang-Mills action is finite. So the integral of the curvature squared extends to this point. So that's why we can extend the solution to R4. But in this case, this is kind of it's almost an elementary analysis. It's just that if the integral of curvature squares is convergent, then you can get an estimate on the curvature, how fast it should decay, and that A, if it does not decay, it decays after gauge transformation.
So I have a similar question then about the convergence of the integrals of B1 and B2. Because a priori, I guess you use the Dirac operator, well, psi plus is L2, and the Dirac operator applied to psi plus is L2.
So this is, I mean, this analysis was meant to convince you that it's convergent, because you see, psi decays as 1 over r cubed. So psi squared decays as 1 over r to the 6, and even if I multiply by a linear function, it still decays as. Yes. Yes. All right. Okay. See you tomorrow.